This is the capacitance. After spherical capacitor, we have another type of capacitor which we call, okay, capacitor is over. Like we have parallel plate capacitor in your syllabus and we have spherical capacitor in your syllabus. Now the thing is, energy stored in capacitor. You need a relation for energy stored in capacitor. Energy stored in capacitor. It's a very small derivation, some 3-4 steps. But before starting this topic, just tell me what is the cause of potential energy?
Parachute interaction.
Sorry, what's the cause of potential energy? Someone was telling. Potential energy. Apit, you were saying something. Or Saifullah. Or Miraj. Interactions. See, we have two types of energies. One is kinetic, another is potential. What is the cause of can you do one thing? Can you all just switch on your video? Sorry, not videos. Position. Just switch on your audios, please. Open your mic, everyone. There would be some disturbance, but that's okay for me. Just open your mic. There will be some background noises, but it's okay. Like some background noises are accepted in class. Okay. And keep this mic on throughout the class. Huh? So what is the cause of potential energy? Someone said that this is interaction.
Yes.
The cause of potential energy is conservative interactions. We have some forces which are known as conservative forces, like electrical force, gravitational force, elastic forces. These forces are conservative. So whenever you have conservative forces, you have potential energy. Gravity is conservative, so you have gravitational potential energy. Electric force is conservative, so we have electric potential energy. Elastic force in spring is conservative, so we have elastic potential energy. So whenever we have conservative forces, we have corresponding potential energies. So when we say that energy is stored in capacitor, you should ask the question, what type of energy this capacitor have? What do you think? Will this capacitor have kinetic energy? Are we talking about the kinetic energy of capacitor?
No, sir.
No, potential.
Not the kinetic, but the potential. But for potential energy, you should be having forces, like electric forces. So how will you explain that two plates of capacitor have electric force? Two plates of capacitor one plate will have positive charge and another plate will have negative charge. Due to this positive and negative charge, they will attract each other. They will attract each other by electric force. So the two plates will have electric potential energy. Clear, everyone?
Yes, sir.
Now the next question is how to calculate that potential energy. To calculate that potential energy, we use the help of work done. The formula for potential energy says potential energy is equal to work done by external force. Now, work done by what? Work done by external force in carrying your system from some initial to final position. Initial to final position. Like if I give you example of gravitational potential energy, I ask you to calculate gravitational potential energy of this pen. The gravitational potential energy of this pen is the work done in carrying this pen from one position to another. So say this is the first position of pen. It's placed over my hand. I take it to another position to a height edge. I did some work and I do some work to carry this pen from this position to this position. The work done by me to bring this pen from this position to this position gets stored in this pen in the form of potential energy. So this is the initial stage and this is the final stage. Work done in carrying body from initial to final stage gets stored in the form of potential energy. Clear?
Yes, sir.
Now you
sir.
understand what is initial and final positions?
Yes.
Yes, sir.
Yes, sir.
But when we talk about capacitor, it's not position. See, I'm not bringing plates of capacitor from one position to another. So when we say initial and final for capacitor, that means initial and final stages. What is the initial stage of capacitor? Initial stage means when capacitor is uncharged. When capacitor doesn't have any charge, then that is the initial stage. What is the final stage? Means when your capacitor is fully charged. So this is the initial stage for your capacitor. Initial stage means This your capacitor is uncharged. There is no charge over the plates of capacitor. Q is equal to 0. And this is the another stage when your capacitor is fully charged, the positive charge, and this is negative charge. Charge is maximum, Q is equal to Q. So this is initial and this is final. So the work done in carrying your capacitor from this initial stage to final stage gets stored in it in the form of potential energy. Now, these initial and final stages are clear, right?
Yes, sir.
Yes.
Okay. If initial and final stages are clear, then the next thing is who will do work done in carrying your system from initial to final stage? There should be some agency. Initial stage means there is no charge. Final stage means your capacitor is fully charged. So there should be someone who is doing work done to charge the plates of capacitor. And what agency is that which charge the plates of capacitor?
The medium.
No, not the medium. Any other answer? If I want to charge a capacitor, what will I do? I give you a capacitor. Yes.
Put electrons or let it away from.
There's one more option, Anshika. How to charge the plates? Not induction. Say in real life, like if I give you a condenser, a capacitor, and I ask you to just charge this capacitor, what will you do?
Sir, we attach to a battery.
You will attach it to a battery. So who is charging the capacitor? Battery is charging the capacitor. So the work done by battery to charge the plates of capacitor to giving 0 to a Q charge to the plates of capacitor gets stored in it in the form of potential energy. Is it clear?
Yes, sir.
So that's the work done by the battery. So this is the process through which we will do this derivation. We will calculate work done by battery to charge plates of capacitor get stored in it in the form of potential energy. In form of potential energy. This work done gets stored in the form of potential energy. Now we have to calculate work done. So to calculate work done, we need a mathematical relation. How we calculate work done in electrostat? Yes, how we calculate? You again switched off your mics. Please switch on your mics. How we calculate work done in electrostat? Any formula to calculate work done? Open question to all. How we calculate work done?
Sir, we had a formula, right? Fs, and then F would be 1 by 457.
No, see, Fs cos theta is when you have force. We had another formula which we write in the form of this potential. We have one formula in the form of potential to calculate work. Alia,
Q into delta V, I guess.
yeah, that's it. Alia, you are right. F external dot dr, we can do that thing, but that would be very, very lengthy calculation. If you choose that path, if you try to calculate work done through the force, then that will take too much time. That will be a lengthy calculation. The easier is this charge multiplied by potential difference. We will calculate work done through this path. That will be easier. So work done by battery to charge plates of capacitor gets stored in the form of potential energy. Initially, your capacitor was uncharged. Finally, your capacitor will have some Q charge. I'm taking a state which is in between 0 and Q. I'm writing at some time t. I'm choosing a stage which is in between the initial and the final state. Initially, your capacitor is uncharged. Finally, your capacitor is fully charged. I'm choosing a state which is in between initial and final. So I'm writing at some t equal to t, some state t, charge on plates of capacitor, capacitor is Q and potential difference across plates is V. So this is the capacitor. Its capacitance is C. The charge over the plates is Q. The potential difference between the plates is V. This is my state at some t equal to T. Now, I want to add some more charge to it. I need work done by cell to add some very small dq charge to the plates. dq charge to the plates. I need work done by the cell to add some dq charge to the plates. That work done will be d done. And how to calculate that work done? That work done is, see, the potential difference is V. Along that potential difference, I am carrying this charge dq. So how we calculate work done in carrying charge dq? Work done is charge multiplied by potential difference. Multiplied by potential difference. And what is the potential difference between the plates? Potential difference between the plates is V. So we write this as dq multiplied by V now. That's the work. So work done is, it's V multiplied by dq. This is work done to carry some small amount of charge dq from one plate to another. So if you want to add additional charge dq to the plates, then your cell have to do some work done, and that work done is this, V into dq. Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Now I need work done to transfer zero to Q charge to the plates. So this is the work done to carry this small charge dq. The work done to carry some large amount of charge is V dq from 0 to Q naught. This is the work done to carry Q charge. It's 0 to Q V dq. Now we can convert this V in terms of Q. This is the relation. Q is equal to CV. So we can write this V as Q by C. So this is V, which is Q by C. So I substitute this V here. So your work done is, it's 0 to Q. V is its Q by C into dq. Now you can take this 1 by C outside. What is the integral of Q? It's Q to the power 1. What is integral of Q to the power 1? See
Q
the
to the power
integral.
2 by 2.
Yes, it's
Q to the
1
power 2
plus
by 2.
1. Yes, over 1 plus 1. And the limit is from 0 to Q naught. It's 1 by C. It's Q square by 2. It's Q square by 2. Limit is from 0 to Q naught. So we can take this 2 outside. So you have 1 by 2C. It's Q square minus 0 square. So this is, it's Q square divided by 2C. This is the work done. This is the work done to store some Q amount of charge on the plates of capacitor. This work done gets stored in the form of potential energy. And you can write this as this is Q square by 2C. This is the energy stored in the capacitor. This is the work done that we are doing to charge the plates of capacitor from this initial stage to the final stage. Just note it down and tell me doubts.
सर अब तक आपने क्या क्या करवाया?
मैं बस स्फेरिकल कैपेसिटर और ये एनर्जी स्टार्ट किया.
सर लिखना कहाँ से शुरू करना?
यहीं से. Yes, written.
No, sir, 1 minute.
Sorry. Written. Noha, Saifullah.
Yes, sir.
So this expression of energy Q square by 2C is in terms of charge and capacity. We can convert it in terms of capacitance and potential difference also. Unib, how will you convert this in terms of potential difference and capacitance? Can you convert charge in terms of C and V?
Sir, Q is V into C.
You can write Q is equal to CV. So when you write Q equal to CV, the energy, the expression of energy is C square, V square divided by 2C. So C and C this cancel. So your energy will be half CV square. That is the expression of energy, which is half CV square. Now, after this, you can do one more thing, like you can remove C also. Ishma, what's the expression of C? Like I want to remove C in terms of Q and B. What will the expression of C? Ishma. Ishma writes C in terms of Q and B.
C is equal to Q by V.
Q by V. So we can substitute this Q by V here. When you make this substitution, we get U is half C, which is Q by V into V square. So square and V will get cancelled out. You will have potential energy, which is half QV. So this is it. U is half QV, half CV square, Q square by 2C. So these are three expressions to calculate energy in a parallel plate capacitor. Note it down. Then we'll do some questions on energy and force.
Can you scroll?
Mhm. Written?
So just a minute. Yes, sir, done.
So the next question is, That's an important question. It says calculate energy density for a parallel plate capacitor. Energy density for a parallel plate capacitor. Parallel plate capacitor. You need to calculate the energy density of a parallel plate capacitor. So this is a parallel plate capacitor. This is plate. Area of the plate is A. These are two plates. Plate area is A and the separation between them is D. You can write volume of the plate as area of cross section A multiplied by D. This is the volume of the capacitor. Area of cross section multiplied by the separation. Okay, what does energy density means? Yashika? What is energy? What do you mean by energy density?
Per energy per volume.
Energy?
Per volume.
Energy density, right? Energy density is its energy divided by the volume of capacitor. So this is energy divided by the volume of capacitor. This is energy density, energy per unit volume. So for a parallel plate capacitor, for the volume of energy of a parallel plate capacitor, I can use this expression half Q square by C. Area of cross section is A, separation between them is D. Minashi, what is the volume of this capacitor which have plate area A and separation D?
L into B.
Not L. A into D.
So you asked what volume?
Volume, na? Area multiplied by the length.
Oh, yes, sir. A.
Right, this is volume, it's A into D. Is it clear up to here? Noah,
Yes, sir.
Alia,
Yes,
clear up to here, huh? Next, what we can do is, do you remember what was the formula for surface charge density? Sigma
Q by A.
Q by A.
by. So see, we want to make surface charge density here. So this is Q square and this is A. If I can make A square here, then you will be having Q square by A square and that will be sigma square. So for that, what we can do is we can multiply it with A in the denominator and we can multiply it with A in the numerator. So this is Q square A upon 2CD into A square. This is Q square A upon 2CD A square. What is Q by A? Sigma. So I just multiply numerator and denominator by A. So Q square by A square is sigma square. So this is sigma square A. I'm using this relation, Q by A sigma, by 2CD into, that's it, 2CD. Now, what is the formula for capacitance of a parallel plate capacitor? Alia? Formula for capacitance of a parallel plate capacitor. How you calculate capacitance?
Epsilon naught A by D.
Epsilon naught A by D. This is epsilon naught A by D. This is capacitance of a parallel plate capacitor. Okay, Alia. So this is C. So we can say that energy density U is sigma square A by 2. Instead of C, you can write epsilon naught A by D into D. D will cancel out this D and A will cancel this A and you are left with sigma square by 2 epsilon. Next, I'm multiplying and dividing by epsilon naught. I'm multiplying denominator with epsilon naught and numerator with epsilon naught. So see what I will get. I will be getting sigma square epsilon naught divided by twice of epsilon naught square. What is the expression of electric field between the plates of capacitor? Does anyone remember the formula of electric field between plates of capacitor? We did this in the last class.
Sir, Q by epsilon.
Very good. Electric field between plates of capacitor. You all check your notes. Electric field between the plates of capacitor E was sigma by epsilon naught or Q by epsilon naught, as I've said. So instead of this sigma by epsilon naught, I can write E. So that will be E square. So you can say that energy density is half epsilon naught into E square. See, I am substituting this E here. Instead of sigma by epsilon naught, I'm writing E square. Is it clear? Anshika? Munib? Is this substitution clear? Instead of sigma by epsilon naught, I'm writing E.
Yes.
So this is expression of energy density, half epsilon naught E square. What this expression shows? This shows that energy density for a parallel plate capacitor is depends upon electric field only. So this shows that energy density depends upon field only. Energy density depends on field, electric field. Or you can say that energy is stored in electric field. In a capacitor, the energy is stored in electric field. Energy stored in electric field. So in a capacitor, the electrical energy is in the field itself. So if electrical energy is in the field, that means it's not confined within the capacitor only. You can have field anywhere in your room. In your room, maybe you are having some mobile phone radiation. This mobile phone radiation will generate some electric field. You can have some charge flowing through the conductor. Through that charge, will be having electric field. So throughout, if you have electric field in any region, the cause of electric field could be many. Charge flowing through the wire, that charge can generate electric field. Your mobile phone radiations that generate electric field. So anywhere, if you have electric field, then in the unit volume of electric field, you have some energy, and that energy is this. This is energy per unit volume, half epsilon naught E square. This is the energy in electric field. So wherever you have an electric field, you have energy, and that energy is half epsilon naught E square. See, what are light waves? Light waves are electromagnetic waves. Light waves have electric field and magnetic field. So 50% energy in light wave is this half epsilon naught E square. The light wave that's coming from your bulb, the 50% of energy in that light wave is from this half epsilon naught E square. Because light waves are nothing but electric and magnetic fields. So this expression shows that energy is not stored in the capacitor. It's stored in the electric field. If that electric field is within the plates of capacitor, then fine. Energy is between the plates. But if that electric field is in some open region, then you have energy in that open region also. So energy is in field. Clear this calculation?
Yes, sir.
Okay, note it down. We'll do more questions on it. Mazia, is it clear?
Yes.
Written, everyone? Muneeb, Noah, Minashi, written.
Yes, sir.
Yes, sir.
Okay. The next question is, note this one also. Okay, next question. The next question is, let's calculate force. Calculate force between plates of capacitor. Force between the plates of capacitor. So these are the two plates of capacitor. One have charge plus Q, another plate have charge minus Q. The separation between them is D. Charge density of one plate is sigma, charge density of another plate is sigma, plus area is A and A. I need force between these two plates. How to calculate this force? Noah, what will be the expression of force? Wow, one is positively charged, another is negatively charged. What is the expression of force between them? Oh, you're not audible. Okay, Noah, just tell me, can I use Coulomb's law here? Noah Akhtar. Can I use Coulomb's law here?
No, sir.
Why not?
Sir, it's not a point charge.
Yes, these plates are not point charges. Coulomb's law is valid only for point charges. These are not point charges. Sheets. One sheet is having plus Q charge, another sheet is having minus Q charge. So this is not possible. Like Q by D square. We can't use this formula. It's not valid. So if Coulomb's law is not valid, then how will you calculate force between them? Miraj, Coulomb's law is not valid. You can't use this relation KQQ by R D square. If Coulomb's law is not valid, then how will you calculate force between the plates? Miraj. Yashika.
Sir,
Sir,
Q
will
into
use
E.
Q into E. Perfect. See, Coulomb's law is valid only if you have point charges. So QQ by D square is not valid in this case. But you can use this expression. You can use this expression, then force is equal to QE. You can always use it. Force between the plates is charge multiplied by electric field. You can always use this expression. So Coulomb's law is not valid, but F is equal to QE is always valid. So this is one plate. This plate will generate some electric field. See, we did this thing that if you have electric field And in electric field, if you place a charge q, then that charge q will experience a force, and that force is QE. So this will generate some electric field E. And in this electric field, you have a charge minus q. What is the expression of field due to a plate? Electric field due to one sheet. Sigma by epsilon naught, okay? Anshika, what is the expression of field due to the positive sheet only? I'm not asking total field, due to one sheet.
Q by epsilon naught D.
No. Field. No, not Q by D epsilon naught. Yashika, field due to one plate.
Sir, sigma by 2 epsilon.
Sigma by 2 epsilon. See, field due to one sheet is sigma by 2 epsilon. Or you can write sigma as Q by A. So Q by 2 epsilon naught. Okay. Sigma by epsilon naught was due to the system due to both the sheets. So when you add fields due to both the sheets, then we get sigma by epsilon. But when you calculate field due to a single sheet, then this is sigma by 2 epsilon naught, Q by 2 epsilon naught A. Now we need force on charge minus. I want to calculate force on this charge minus. What is the expression of force? Yes, what is the expression of force on acting on this charge minus Q? Force will be QE. So this is Q. For field, I can substitute here. So charge is negative, so put minus of Q. This negative sign will give you direction. It's Q square by 2 epsilon naught A. So you can write this as minus of Q cube by 2 epsilon naught A. So the force between them, F, is minus of Q cube by 2 epsilon naught A now. That is the force between the two charges, two plates. Is it clear? Now, this negative sign tells the direction of force is opposite to that of field. So the force is acting in this direction. Here also, force is acting in this direction. So both the plates will attract each other. Do it. Any doubts? Minashi? Munib?
No, sir.
Do it. Yes, no. See, no, you need to calculate force between the two plates of capacitor. I can't use Coulomb's law because plates are not point charges. So what we do is we calculate field due to a single plate. Field due to a single plate is sigma by 2 epsilon naught. Sigma is Q by A. Huh? Then we use this expression that force is equal to QE. So I just multiply this field with this negative charge, minus of QU. Okay, Nama?
Yes.
Sir, please scroll down.
Mm.
Sir, how did Q square come?
Yes. See, there are two Q here. This is sigma by 2 epsilon naught electric field, which is Q by 2 epsilon naught A. Force is QE. So one Q is here. Another Q is coming from this field. Oh, sorry. So sorry. No, sorry. So it's Q square. This is Q square. Yes, written.
Yes, sir.
So the topic that we did today, there are not many type of numericals on this topic. Most of the numericals that we get in capacitors are based on series and parallel combination. We'll be starting series and parallel combinations from the next class. But solve this question.
Sir,
Yes.
sir, I don't have access to the mobile phone right now.
Okay. Is your webcam working?
Yes, sir, it works, I guess.
Okay, then just show me your sheet. Huh?
Okay.
So you have solved. Do it. Solve it. Send this on the WhatsApp number of the of Learnivio. See, the second part we have already solved, na? This NCRT problem. We have already solved the second part. Huh? So no need to send the second part. Just send me the first part. Then we'll do a conceptual problem. I'm waiting for your answers. Solve this question. Take a picture from your mobile phone and WhatsApp it to the official number. Or if you want, you can show me directly.
Sir, what's the value of epsilon naught?
Yes, done. Akshat, sorry, Arpit, Anshika, Alia. Okay. Okay, Alia. No, Anshika, this half CV square and half epsilon naught E square are not equal. Half CV square is the full energy, okay? And half epsilon naught E square is energy per unit volume. Second step is wrong. So if you are calculating using half epsilon naught E square, Anshika, then you have to multiply it with volume also. You're going in the wrong direction. Is it clear, Anshika?
Sir,
Yes,
is it
sir.
visible?
तो सर फर्स्ट स्टेप के बाद डायरेक्ट थर्ड वाला स्टेप लिखना है क्या?
हाँ, first के बाद directly. Next is no half CV square epsilon naught AV square. Yes, no is correct. Just 1 minute, Arpit, I can't see your video. Yes.
So
अबे थोड़ा करीब लियो यार इसको. Just 1 second. C is epsilon naught A by D half. Again, you're using CV square. Okay. Okay, Arpit, correct. And what about the rest? Cephala, Minashi, I get the answer. Minashi, this is capacitance, hai na? You're supposed to calculate energy also. See, the expression for energy is half CV square. Half CV square. So your C is epsilon naught A by D. So you can write that your energy is half. It's epsilon naught A by D multiplied by V square. Now you can substitute the values. It's half. Epsilon naught is 8.85 into 10 raised to the power minus 12 into area of the plate, that's 90 centimeters square. So it's 90 into 10 raised to the power minus 4. V, voltage is 400 volt. 400 square divided by D, which is 2.5 mm. This much of joule. Is it clear? Yes, Yashika, good. It's straightforward thing. Yeah. Okay, so once you know these relations, this energy, you know how to connect capacitance with energy. The next thing that you can do is, there is one conceptual question. The question is, he says that you have a parallel plate capacitor. You place a dielectric within that parallel plate capacitor and you connected the battery. Yeah, he will ask you to compare the capacitance of the capacitor before and after inserting the dielectric. He will ask you to compare the electric field inside the capacitor before and after connecting the battery, or before and after introducing the dielectric. He will ask you to compare the energy before and after introducing the dielectric slab. So that is a question, but I am making a table of it. There's 4 or 5 conceptual questions. We'll do it in a table. So this is the initial stage. In the initial stage, you have a parallel plate capacitor. Parallel plate capacitor. With air in between plates. Air between plates. And cell of voltage V0. So this is the initial condition. You have a parallel plate capacitor with air between the plates and a cell of voltage V0. So this is a parallel plate capacitor. The medium between the plates is air. And it's connected to a cell. Voltage of the cell is V0. This is your parallel plate capacitor with air between plates and cell of voltage V0. So what is the capacitance? Capacity is, I call it as C naught. This is epsilon naught A by D. If I ask you to calculate charge or the voltage across the capacitor is equal to voltage of the battery V naught. If I ask you to calculate charge, then charge Q naught is C naught V naught If I ask you to calculate energy, then your energy will be half C naught V naught square. So these are the initial stages. See, you have initial capacity, you have initial voltage, you have initial charge, you have initial energy. This is the initial condition which will be given in the question. He will ask you to calculate all these terms if a dielectric slab of dielectric constant K is inserted between the plates, and battery remains connected. So what you do, you take this capacitor, you introduce a dielectric slab of dielectric constant K, and you did not remove the battery. Battery is connected. So remember one thing, if battery is connected to your system, then voltage will not change. Anything can change. Charge can change, capacity can change, anything can change, but not the voltage. Potential difference will be constant. Potential difference will be constant. Potential will remain constant. Just write this thing somewhere. Like if battery is connected to your capacitor, then everything, every quantity can change. Charge can change, energy can change, capacity can change, but not the voltage. Voltage will always remain constant. Voltage will never change. So in the question, it will ask you to calculate capacity. We'll say, okay, the capacity in air is this epsilon naught A by D. What will be the capacity if a dielectric slab is inserted between the plates? What will be the capacity, Mazia, if I introduce a dielectric slab between the plates of capacitor? Muneeb, what will be the capacity if I introduce a dielectric slab between the plates? Ray? Saifullah, what will be the capacitance if I introduce a dielectric slab between the plates?
Sir, E will, E will be there. So the
I'm
E
asking
will be,
about capacitance, Maharaj. When the air is between the plates, capacity is epsilon naught A by D. When the dielectric slab is between the plates, what is the capacity?
sir, K by D.
K epsilon naught A by D. And what is epsilon naught A by D? That is C naught. So it's K C naught. So capacity increases. Second, voltage. Voltage will remain same because battery is connected, so voltage will not change, it will remain same. Third, charge. Q is equal to CV. How much is C? C is KC naught into V naught. How much is C naught V naught? C naught V naught is Q naught, so that's KQ naught. Fourth, how much is the energy? Energy is half CV square. So charge increase. See, earlier your charge was Q naught. Now your charge is KQ naught. Your charge have increased. Energy is half CV square. How much is C if I compare with the initial case? C is KC naught. How much is V? V is V naught. So that is half. Instead of C, you can write KC naught. Instead of V, you can write V naught. Half KC naught V naught square. What is C naught V naught square? That's U naught. So energy is, see, this is K multiplied by this entire term. How much is this entire term? That's U naught. So that is K U naught. So if you introduce a dielectric between the plates of capacitor and you remain the battery connected, battery remains connected, then capacity will increase, voltage will remain constant, charge will increase, and energy will also increase. Note it down. Let's have one more part that we will discuss in the next class. In the next class, most probably we will finish this chapter. It's just series and parallel combination is left. We'll finish it. Then we will take one more lecture for this chapter and we'll be discussing some topics which are in JEE and NEET but not in CBS. But that's 10-15% more. Yes, Cephala, you are also correct. Huh? Your answer was also correct. Cephala, when you use small u, that small u means energy density. So when you are writing energy, use capital U, okay? Small u means energy density.
Okay, sir.
Use capital. Can I scroll it?
No, 1 minute, sir.
Aisha, I'm just finishing this class. I'm starting in just 1-2 minutes with you. Just 2 minutes. Can I scroll it now?
Yes, sir.
Sir.
Written, everyone? Puneet, Jessica, Noah.
Yes, sir.
Yes.
Yes, sir.
Okay, so we'll stop here. On Wednesday, we will continue with the series and parallel combination of capacitor. And let's see if we can finish this chapter in the next class. I'll stop here. If you have doubts, we can discuss. Class is over. If you have doubts, we can discuss.
सर एक बार थोड़ा स्टार्टिंग का दिखा दो स्क्रीनशॉट लेना. Yes, sir. Daily. सर इतना ही था बस.
बस इतना ही था. इसके आगे आपने लिख दिया था.
ओके सर, थैंक यू.
Thank you, sir.
Okay, sure.
Thank you, sir.
Thank you, sir.